So, shall we start? So, we talked about convolution last time, right? So, what was the idea of convolution? So, why we use convolution, why we went for convolution? Because what did we want to achieve to replace, by replacing fully connected layers with convolution? Less weights, exactly. So we wanted to reduce the complexity of these layers by reducing the number of weights. We just came up with this idea that convolution is a kind of nice linear transform, which is essentially looking like a sort of sparse linear conversion, right? So this was the idea. And then we said like we can essentially use convolutional neural networks to, yeah, this one works. Okay, so maybe I should use always this one. So we said that we can use convolutional neural networks or convolutional layers instead of fully connected layers to do the linear transform and then activation. So let's just have what we want to do today. We want to just complete this idea of convolutional neural networks so you can see how a CNN look like, and then we're gonna take a look at a few CNN architectures, known ones, and then we try to just decipher what is written inside the diagram, so hopefully you just see what is happening there. And then we're going to talk shortly then about the sequence data. So once we are over with CNN, it's essentially over with everything we had in this lecture. And then, as I told you last time, since we have some time, I'm going to just cover a bit of sequence data today. So I just give you a brief idea of what is recurrent neural network, why we do that actually, and like what you should wait for if you just go that direction. And then next session we're going to talk a bit about reinforcement learning and generative models in general again. So let's just start with a quick recap. So we talked about doing the training, building a neural network and doing the training on it, right? So if you want to do classification with a neural network, what should we do? So you could have anything in between. The input should match the kind of data that you are giving to. And what should you do to the output? What do you put as the activation of the very last layer? The output layer, if you are doing classification. Softmax, right? So you're going to put a softmax, the number of outputs that it has is corresponding to the number of classes that you have. And then essentially looking at that one, you can try to just compute some loss using, what is the loss function? Classical loss function if you're doing classification. Cross entropy, great. So you're going to select some loss function, and then essentially you set your model given the problem that you have, and then you do training. And by training, it simply means that you go for a specific number of epochs. In every single epoch, you're actually doing lots of mini batches. After every single mini batch, you update your weights. And once you're totally over with the whole epochs, then you're going to be over with your training. You're going to get your trained weights. So this W star here is essentially the trained weights. Now, if you train it, if you get your trained weights, what is the next step? What do you do? After you trained your model on the training set, what you do? Validate it, right? So you're going to go and validate it. So the data that you have contains training data, validation data, and test data. You train it on your training data set. And once you're over, once you got your trained model, you're going to validate it. Meaning that you just take those samples inside the validation set. You just check how the loss look like. So if it looks fine, so similar to what you got after training, then you're fine. If not, then you are going to play with the hyperparameters. This is the hyperparameter tuning. You keep doing this till you see the same validation as you get after every training. And then once you see that, you're going to check the generalization at the very end by testing your model, right? So test is not giving you any feedback. It's simply evaluating, making sure that your hyperparameter tuning is again not making overfitting on the validation set. So we talked about this last time. We also talked about the general idea of generalization. So in generalization, we are looking for having a model not simply trained and working well on the training set, but rather generalizing. It means that when you get a new sample and you give it to this model, you see roughly the same thing as the true label that it has. And if the model generalizes, you hopefully see something like the one in between. So you're going to see a kind of fair, balanced trade-off between the error that the model gives you in the training and testing. But if you see overfitting, then you're going to end up with something on the right-hand side, right? So your model is going to perfectly match the data that you have. So it's going to pass over every single point. Very small training error, but when you test it on a new sample, you're going to see a very large error, which is the idea of overfitting. And then we talked about different approaches that we can come up with to just prevent or reduce, in fact, overfitting, right? So we talked about this. We also talked about this generalization error components. So the key trade-off between the variance and the bias. So any generalization error, you can essentially write it down in terms of bias. And the bias is how your model is in average different from what the true label is in average, right? So the difference between the output of your model and the output of your true label, in average, this is what we call it bias. So we can try to push the bias to be very small, but doing this could essentially increase the variance of your model, right? So it's going to make your model vary a lot, much more. And this is when you start to see this overfitting, right? So there is a kind of sweet point between the two things, and that is something that we're going to find it by hyperparameter tuning, or hopefully with different other approaches that are controlling overfitting, like regularization. And there's also always one minimum error that we have in this generalization, for generalization, which is dictated by the model source properties, so source distribution, model data distribution. You cannot control that guy, right? So that one, you can never go below that one. So if you see like extremely good result in training, it's a bit fishy because it might be the case that in generalization you start to see a huge error. So that was the thing that we talked about, and we got over with the whole idea of generalization. We started with the idea of convolution, right? And for the convolution, we started to look at the, mathematical convolution, that commutative linear operation that we have. But we said, like in practice, in neural networks, we don't need that one. So we don't need to flip the filter. We just use the filter itself, right? And then this was actually the convolution. So you remember that. You remember how we compute convolution, right? So you're going to get your filter. Your filter is smaller than your input. So the input could be your input image, right? And this input could have multiple channels, right? For instance, in this example, we assume we have 3 different channels corresponding to the red, green, and blue channels of your input image, right? RGB image you have 3 different channels. Then you get a filter. The filter has the same number of channels at this input, but it's smaller. So if your image is of size, say 10 by 10 or 100 by 100, then your filter is much smaller. So for instance, it is, I don't know, of size 7 by 7, right? And then it could be like in 3 dimension, right? So it could be multiple channels, as I'm showing in this image. So it could be multiple channels. So you have 1, 2, 3 channels. And then this guy is smaller. Then you start from this point, right? You put your filter here. You multiply everything inside your filter with the corresponding things inside your input. and then you sum them up, right? When you sum them up, you end up with what? What's going to be output? It's going to be one single scalar, right? So you're not going to have multiple scalars or a vector. You are going to have one single scalar. So you get that as scalar. You're going to write it down in one map at the output, right? And then you start sliding this guy over the input. So I get this filter, and then I slide it over the input gradually. And each time that I slide, I get a bunch of new numbers. I just do the multiplication, add up everything, and then write it down on the right-hand side map, right? So once I keep on going like this till I'm over, so I start from top left, I end up at the bottom right, and then it's over, right? So the convolution is over now. Now, this is the idea of convolution, and we talked about this, that convolution is essentially like a linear operator or linear layer, which is not fully connected, right? So for instance here, this is the example we ended the last lecture with. So here, as you can see, you have weights W1 to W4, and when you are convolving it with this input, you essentially get these guys, put them on the first subpart of your input image, or whatever that is, and then you multiply them, and then add them up. So you can think of the output, which I'm showing them by Z. So you can think of the first output, Z1, to be essentially weight 1, which I'm showing it by a red color here in the right-hand side diagram. So weight 1 multiplied with by the first guy, first input. Weight 2, the blue one, multiplied with x2. Weight 3, the green one, with x4. Weight 4, the yellow one, with x5, right? Yes?
So what we have on the last slide is basically the same thing as this slide, right?
Yes.
But it's just that the other one's considering 3 dimensions as opposed to the one here.
Exactly. Exactly same thing, exactly. So what you have, you can think of these two maps, I mean the filter and the input map, both of them, to be like 3D objects, right? So they have multiple channels. There's nothing going to change. Yeah.
So just the whole principle, they all feed into one neuron, pretty much. Like in the last slide, for example.
This one?
Yeah, you would have 9 inputs in a neuron, pretty much.
Not 9, 27 actually.
Okay, yeah, my math is wrong.
3, yeah. 27 weights you have, then you select the first 27 pixels. You just do the multiplication, add them up, you get one scalar, right? And then you just shift it once to right, and then again, the same ways kind of get multiplied with new parameters. Some of them are the same thing as we had before, a bunch of them are new, right? And then you keep on doing it. Yeah. So again, here is the same thing. So I put these weights here, so I start from there. I can compute Z1 in this form, then I keep on going forward, right? Just I shift the filter, I just do the computation again. Again, I can think that Z2, which is the output of the convolution, when I just convolve the filter with this part of the image, of the input, this is going to be, again, a linear combination of those pixels. And I can keep on writing down the same way. So every time that I slide these weights, I am just looking in a subpart of it, and I'm computing a linear combination of that subpart. So at the end of the day, I can look at this whole process of convolution as a kind of linear mapping, which starts from X, computes a bunch of linear transforms on these subparts of X, and computes Z1 to Z4. So this is a linear layer or linear operation, but the linear operation is not fully connected, right? So it's sparsely now connected because, for instance, x2 is not connected to, or x3 is not connected to z1, for instance, right? So not everybody is connected to the other. This is one point, and the other point is that they are sharing parameters, right? So we indicated this one as well. Red guys are all W1, green guys, blue guys are all W2, and so on. So you essentially are doing this linear transform with simply 4 weights, which is much less as compared to a fully connected layer, right? If you want to do it fully connected, then you have 9 weights, 9 inputs here, 4 outputs there, so you essentially have 36 different weights, right? And you need to train all of them, but now you only need to train 4 weights, which is much simpler task, right? So this was the idea of CNN. And what I want to do today, I want to just finish the convolutional neural network. So I give you the big picture, the overall approach that you can use it, implement one convolutional neural network and use it for some visual tasks. Then once we are over, I am going to just take a look, start with this, last overview part of the course where we try to just look into some, more advanced topics in machine learning. Today we are going to talk about sequence data. Essentially, we just talked about RNN, but next session we're going to have more. So we're going to talk about the reinforcement learning and generative models. So everybody's cool. So anybody has a question from last session? So the convolution idea is clear for you, right? So you now are familiar with the idea of convolution, right? So the whole idea of convolutional layer, as I mentioned last time, is that you get this convolution. So you get your input, you do the convolution. You do know that this convolution is essentially a linear mapping, right? And what we do in feed-forward neural networks, in the fully connected networks, we start with a bunch of input. We do linear mapping, then we activate, right? Again, we do another linear mapping, and we activate and keep on doing this. So now the idea is that instead of using fully connected, basic linear transforms, why we don't use the convolution, which is a sparse one with shared parameters. So this is a much easier way, or much easier thing to train. So one convolutional layer is essentially that you get your input, you convolve it with a filter, and that filter is in general a bunch of weights which you can design. So they are the parameters that are specifying your model. You are going to train them at the end of the day. And then whatever you get at the output map you get, you just activate it, right? So you pass every single entry inside that output map from one nonlinear function, right? And this activation is crucial. You need to have, again, nonlinear function, because from a couple of lectures ago, you do know that if you have a linear activation, this is not going to do anything, right? So again, if you have a convolution after convolution after convolution without activation, it looks like a one giant convolution, right? So it's useless again, right? So you always need to activate after every linear transform. So this is why we do it here. Now, if you want to have a better picture of one convolutional layer, this is going to look like this one, right? So you're going to have a filter which is of smaller size as compared to what you are giving as the input. And this filter has a bunch of weights which you can train. It's going to just slide over the whole input that you have. Then after doing this slide, it's going to compute a bunch of values, right? So every single pixel inside the output map is essentially one single output of your convolution, right? Once your filter is located on one specific place, right? And then once you computed that convolution, you're going to activate it, right? For instance, ReLU function. ReLU is the most famous activation that you got for CNNs. Okay? Everybody's clear? So now question, how many weights do I have in this convolutional layer? Why 9? So the input is 3 channels. It's 27, right? Yeah, 9, yeah, 3 by 3 by 3, yeah, it's 27. So you're going to have 27 different weights, right? Okay, so say that I get so I'm going to show it like this. So this is what we call a tensor. So we essentially have tensor now, or image is a tensor, so it looks like this, right? No. So it's going to look like this, and then every single channel is like a map, right? So you're going to have lots of these maps. All of them going right like this, right? So every single of them is one map. So on. Now, say that this tensor that I have, it has 3 channels. It has, for example, I don't know, 100 pixels here. It has also 100 pixels here. And then I start doing convolution. So I put my filter here on 3 by 3 by 3 part of it. I just do the multiplication and addition. Then I'm going to have one scalar, right? So I'm going to take that scalar. So say 1, 2, 3, 1, 2, 3. So this is what I'm going to look at. So this part is going to be the part that I'm going to look, right? And then I just do the whole product, do the addition, and then this is going to be one thing at the output, right? The first value on the output map, right? Then I get this guy, I just slide it once to the right, so now I start from the first one, I end at the 4th one, and then I have another guy, right? So 3 by 3 by 3, everything as before, and now again I do the multiplication, I do the addition, and again write it down in the next cell, right? And I keep on going till I'm finished with the whole. I mean, my filter is exactly here bottom right, okay? Now, what is the dimension of the output? Say the input is 100 by 100, and for simplicity, let's assume that I do what we call a zero padding, meaning that I don't start exactly from here, but I just add a bunch of zeros, so that the map that I make at the output is exactly, again, 100 by 100. Okay? If I have this 100 by 100 map, how many of them I do make after doing the convolution? When I'm finished with the whole convolution, how many of those 100 by 100 maps I do have? 1. I'm going to have just 1, right? So don't get confused. I'm not making multiple channels, right? Everybody's clear? Yeah? So don't get confused. We are just making one single map. This is why the output map that you see here is just one map, right? It's one channel. You're not going to have multiple channels. You're just using one single filter, right? So that filter, wherever it sits, it's going to get multiplied with anything inside it. And then you add everything up, you're going to end up with one number, right? One scalar. And that scalar cannot make multiple channels for you. It's going to be just one number in this output map. So convolving the filter with your input going to end you up with one map, right? Okay? Everybody's clear? Okay. And now, once I computed everybody here, the numbers here, the next thing that I'm going to do, I'm going to pass every single guy through one activation, right? So you might have your ReLU function here, and then you're going to give this whole map into this ReLU, and you're going to get exactly the same map at the output, only you have replaced for every negative value 0, right? So anything that is negative, now you're going to replace it by 0, right? But at the end of the day, you have one map. So I hope that is completely clear for you. When you are convolving a filter with any number of channels, with the same input, with the input with the same number of channels, then you're going to end up with one map. You're not ending up with multiple maps or a multi-channel output. So your output is a matrix object. The input is essentially a tensor object because your filter is a tensor object, and your convolution is just somehow computing this inner product, which ends you up with one single channel. Okay, so now what if I want to have multiple channels, right? Because if you have some experience with CNN, you do know that the output is just always getting larger in the number of channels, right? So how can I make multiple channels? I can use multiple filters, right? So I'm going to have one filter computing the first map for me, right? Then I'm going to have the second filter computing another one. So here I have one filter, right? So one tiny filter I could have. And then I'm going to put one other filter here. Again, I'm going to get the same input. I just convolve it. I'm going to end up with the next map, right? So if I want to have 4 different maps here, I'm going to use 4 separate filters, right? And each of them is of dimension. Look at this image, and you tell me. What is the dimension here? So the input is 3 channels, so definitely this guy has also 3 channels, right? And then every single of them is 3 by 3 filter, meaning that every single of them has 27 different weights, right? Now you have 4 times 27 different weights now, right? Because you have 4 different filters, every single of them has 27 weights, and these weights are independent, right? They are different parameters that you can't train all of them. Clear? Everybody's clear? Questions? So now, here in this image, as you can see, I have this orange guy, for instance, is going to sit on this guy first. For example, this part that is somehow highlighted in the image. When it's sitting here, it's actually covering that 3 by 3 by 3 subpart of the input, right? And then once you multiply everything, you're going to end up with one number. This is going to sit on the other side in one of the cells, right? The guy next in front of it is being computed by the second filter, right? So the second filter goes and sits exactly the same place at the input. You do the inner product, you do the summation, you're going to end up with one other number, then you write it down next to that one, right? And you keep on doing it till you're finished with all of your filters. So here you have 4 different filters, so every single of them is computing one of these points, so you're going to go 4 in depth, right? So your output, as you can see, it's the same size as the input, but now it has 4 different channels, right? And it's because every single channel is computed by a separate filter, right? Everybody's clear? Yeah. When you want to increase your number of features, right? Because your input is probably a very rich image, right? And then you want to just extract any features inside it. So you want to gradually increase the number of features you are getting from the image. So if it is like 100 by 100 by 3, RGB image 100 by 100, you essentially have 30,000 pixels, right? So now you need to just increase or compute much more number of features as compared to this 30,000, so that you make sure you are grasping everything inside the image, right?
When we did it with one channel, we basically just use one hidden layer realistically to represent convolution, right? Just one hidden layer.
Yes.
But when you have multiple channels like this, does that mean you're considering more than one neural network?
No, this is one channel. Sorry, this is one layer. Yeah, one layer has multiple convolutions. Yeah.
So you would take like the same input position and link it to 4 places.
Exactly. Yeah. So the same sliding that we did on the board. 4 of them, exactly. And once you're finished with the 4, you have 4 maps at the output, right? You again can think of it as one image with 4 channels, right? And then this is the output of your first layer. Then you again give it to another convolutional layer. It does, maybe this time it computes 8 channels at the output. So you're going to get much larger. You keep on doing it till you have enough features that you can start doing classification or whatever you want. So, everybody's clear about this multi-channel convolution idea? So, now this is one hidden layer, or one convolutional layer that you could have. Meaning that your convolutional layer is containing multiple filters. It's going to compute multiple channels, multiple maps at the output. all of these maps are activated, right? And you can have the same activation for all of them, right? Okay. So this is going to be the convolution. Next thing that we typically do inside convolutional neural networks is the idea of pooling. So we're going to pull things out of what we have done or we have collected by convolution. So when you are doing convolution, so let me just get back here. So if you have multiple channels, so here I have 3 guys at the input, 3 different channels. I am computing 4 channels, right? And as I told you, you are going at the end of the day to just compute lots of channels, right? But now that you are increasing the number of channels, this means that you are just getting too much features, right? At some point, you don't need all of them. So you want to somehow get rid of some of them, right? And how you can do it, we typically do it alongside with pooling, the idea of pooling, okay? Now, let's see first what is the pooling. So the idea of pooling is that if you have one map at the input, then you can just go exactly like the convolution over this map, but this time you just compute one fixed function of everything inside the window, inside the filter. For instance, this is the example of max pooling, pretty much the most common example we use in practice. And the whole idea is that I have one filter. Typically, the filter is the same size of the convolution filter that I did before pooling. Like in my example, it was 3 by 3 filter. So I'm probably going to use the same 3 by 3 pooling filter. And this guy has nothing inside it. The blue filter has nothing inside it. It's going to look out into the window, and it's going to collect the maximum value inside that. Okay? So for instance, here, what it does, it's going to look on x11, x12, x21, x22, all of these 4. And out of this 4, it's going to just compute the maximum value of this window, right? And then it's going to write it down at the first place output. Okay? Then it's going to go to the right once again, exactly like the convolution. Same behavior as convolution. This time, you don't have weights to just compute those linear transforms. You simply do one simple operation on that. So you just go next, and again, you look at this window. You just collect the maximum value inside the window. You're going to write it down next in your pooling output, right? And you keep on doing it till you're over with everything inside your input filter. Everybody's clear? Questions? No question? So let's just do one example. Say I have this input map. Okay, and I want to do max pooling on it. My filter is 2 by 2. Okay, how can I do it? Look at this window, the window that I'm showing by red. What is the maximum value there? 3.2, right? So I'm going to write it down as 3.2 at the first location on the output map, right? So what's going to be the next guy in the output map? Any idea? It's going to be, again, 3.2, right? Because when I go next, again, I'm going to look into this window, and everybody inside this window is smaller than 3.2, right? The maximum value is 3.2. I'm going to go next. Now I'm going to have 2.1. Here I have 1.5, and so on. You can keep on going till you're over. So once you're here, you're over, right? So you have collected, you're over with the whole input map. In every single slide, you are looking and taking the maximum value, right? Now, one thing. Look at the input values here in this blue map here. And then look at this green map and tell me which one is fluctuating in values more. The blue one, right? The blue one is fluctuating more, right? So you see the value from 0.4, it jumps to 2.3, but here 3.2, 3.2, right? From 2.3 jumps to 0, here just slightly changes to 2.1, right? And you can't guess why this is happening, right? Because each time that you are looking in the window, you don't deal with the number itself. You just take the maximum in the window, right? which is just reducing the chance of high fluctuation, right? So this is the main purpose of pulling. So the pulling is just trying to kill all of those fluctuations inside your input. So you usually do it after you do the convolution. So you do your convolution, you compute your output values. You know, these values could just jump up and down a lot, right? Then if you do a pulling on it, this pulling is going to somehow filter out. It is going to smooth out your convolution output. And this makes sense. I mean, that we're going to use this kind of approach, like computing one fixed function, because this fixed function is going to just each time not look into only simply into the number itself, but everybody around it, and this is going to reduce the chance of high fluctuation. Okay? So this is, for instance, max pulling, and you could also do other forms of pulling. So in general, you can just put, instead of max or mean or whatever, you can put any function. But max pulling and mean pulling are the common ones. So what do we do in mean pulling? In mean pulling, we again do the same thing. So we slide again with the window, but instead of computing the maximum value, we just take the average value. Okay? So for instance, I look at these 4 values, you just sum them up, divide them by 4, and then I am going to write it down at the first place, right? So again, I just slide the window, I look at that window, I just average everything inside it, and write it down in the second place, and I keep on going till I'm over with the whole pulling. Clear? Questions? No question? Great. So same example. If we go for the same example, this time you should just look at those boxes and you just add up everything inside the red window. You divide them by 4, right? And then if you do it, again, you can just do the computation as before, right? So each time you just sum them up, divide them by 4. And again, if you just keep on doing the numerics, then you're going to see that the variation again at the other side is less than the one at the input, which again makes sense. I mean, averaging is a kind of low-pass filtering of your image, right? So essentially what pulling does is just filtering, again, your output of the convolution by a sort of low-pass filter, which is reducing the variation inside so the high-frequency behavior of that image. Everybody's clear? Questions? So these are the 2 key operations inside the convolutional neural network. Convolution itself, plus activation, which makes the convolutional layer, and pulling. Pulling is the other one. Okay? And we just did everything here by what we call it a stride 1. And what do I mean by a stride 1? When I was doing, for instance, here pulling, when I was here, I was shifting everything just once right. Correct? So I didn't jump anything. I didn't just skip anything in between. Correct? So, for instance, again, when I was here, I wanted to come down to the left. I didn't just jump the whole way down, so I just came 1 down, right? So 1 row down. 1 row down, and whenever I want to just go right, I just go 1 column right, correct? This is when I do everything by a stride 1. And when I do by a stride 1, this means that if I do enough zero padding around my input, then whatever the input is, the size of the output, the map size, not the depth, the map size is going to be the same thing, right? So I'm not going to change the size, meaning that if I get this big map as the input and I do the convolution with 1 filter, I am going to have pretty much the same size at the output, right? But as I told you, once you do the convolution, you are just going to increase the number of channels. And to just get rid of some features in between which turn out not to be very important, you need to just get a bit of less features, right? So you want to increase the number of channels, but you want to shrink the size of every single channel. Now, how you can do it, you can essentially do it by pulling with a stride more than one. Yeah? So you can do it with, for instance, here I'm doing it with a stride 2, meaning that when I start here, so you see top left, this is where the window is, but when I want next do the pulling, I'm going to do it with a stride 2, meaning that I don't go right away to the next column, I just jump one column in between, right? So I'm going to go for the second one, right? The second next column, correct? And again, I'm going to go for the second next column, and so on, till I am over, right? So once I am over and I want to come down, then the thing that I'm going to do is that I am not going to just go right in the row below, but I'm going to jump two, right? Jump one in between. And it's going to be like this, right? So you got the idea of how I can do it with a stride. And once I do it with a stride, I am going to shrink the size of my output, right? So the output that I get here is no more of the same size here, but is of the size half, right? Half times half. So I'm going to drop 1/4 of the samples. And this is helpful because I am going to increase the number of channels, so I get more and more maps at the output, but I want to have somehow limited number of features, so I can just drop the number of features inside every single map. Everybody's clear? So you got the idea of stride, right? So it's a kind of sampling. Great. So that's it regarding the stride. And once you have a convolution layer plus a pooling layer, then this is what many people call it a sort of complex convolutional layer or complex convolutional unit. What that means that you get the input, and then you do maybe with multiple filters, you compute multiple features at the output. You can potentially do some pooling on that, like max pooling or mean pooling, to make everything smooth. And then you can do sampling, so you can have some stride to get the size of every single map at the output smaller. And you can repeat this over and over and over, right? So you start with 3 channels. 3 channels, 100 by 100. Next time you compute 5 channels, 50 by 50. Next time you compute, I don't know, 30 channels, 25 by 25. Next time you compute 60 channels, 8 by 8, I don't know, whatever, yeah? 5 by 5, say a factor of 5. 5 by 5, and then you're over, right? So you have lots of channels, and each of them is very small. Clear? So this is one convolutional unit. Some people, like for instance in the textbook by Goodfellow, the deep learning book, they call it complex unit. And the term complex unit comes from the visual cells of like intelligent creation, biological visual cells. Because the computational model we develop for them is, for our visual cortex, is that when we see something, we have a bunch of simple cells. They are like those maps inside the image. And then we get that. We just do a linear operation on that. So we get the output convolution. And then somehow something inside our visual cortex is just doing the activation, pulling, and sometimes sampling, right? And then you're going to get at the very outputs bunch of new channels. And these channels are maybe of a smaller size, but of some sort of processed feature. And since this in the initial modeling was called complex cell, this is why people call it also a complex convolutional unit. Whereas if you think of the convolutional layer as a single unit and the pooling layer as a single unit as well, then it's going to be a simple convolutional layer. I mean, it's just a terminology. It's not really something important. So, but a complex convolutional layer is simply one convolutional layer which could potentially compute multiple maps at the output, and then you would do some pooling on top of that, right? So you can do some pooling on that, which does the smoothing and also drops the size of your maps inside every single channel. Clear? Questions? No question? Okay. Okay, great. So if you got no question, then let's go ahead and define the CNN. So one CNN, one convolutional neural network, is nothing but one cascaded version, exactly like what we do in the fully connected neural networks. So you're going to get these complex convolutional units, and you just cascade them right after each other, right? So this is going to be a convolutional neural network. Okay? So essentially, you can get one of these complex units. So here you have convolution, here you have pooling. You can do essentially, you can repeat this multiple times, right? So L different times. And once you're over, once you have enough features that you wanted, the next thing that you are going to do is the thing that we call it flattening. So do you know what is the idea of flattening? So once you do multiple convolutions, then at the very end of the day, you are going to end up with, I don't know, 30 different channels, right? Now, these 30 different channels are 30 different matrices, right? Now, what we want to do next, we want to get everything inside these 30 different channels and give all of them into one big feed-forward neural network, one classic simple MLP. So what should we do then? We should get these guys and put them right below each other, right? We just write it down in a form of a vector input, right? This idea is what we call it flattening, so nothing specific. In Python, you also use the same method, right? So when you have a tensor, if you have a list, then you can write dot flatten. Or like in PyTorch, you write dot flatten, and then you can just make it into a single list, right? So this is the same idea here. So you do the flattening. Once you have done the flattening here at the output of your last convolutional layer, you're going to have a vector of values, right? And now that you have this vector of values, next thing you are going to pass it through one fully connected neural network. Clear? So now you can do it because you have a bunch of features which are processed very well. So it's just grasping the key things inside your image. You didn't need to give your whole image inside your neural network at once. You just processed it. You got good features out of it. And now you're just giving it to the feed-forward neural network here at the very output to just compute the class of your image, for instance, right? Everybody's clear? Questions? So, say I am doing a binary classification. So my images are cat or dog, okay? What should be this output layer? What is this guy? What should I put here? First of all, how many outputs do I have? Just one. Binary classification. Yeah, you can do two, but then always the probability of one is one minus the other one, right? Yeah. Okay. And then how do you activate it? A sigmoid function, right? So now if it is like, say, 4-class classification, it's going to be 4 and a softmax, right? Great. So now, one thing else. Assume that instead of this fully connected neural network, which I'm showing here with 2 different hidden layers, I am just having one output layer, okay? When I do one output layer, what is that last output model? What did we call it? So if I don't have any hidden layers, so I get my x's, and I directly map them to the output by one linear transform. What is it? It's a linear model, right? A linear classifier, correct? The output is going to be a linear classifier, correct? Now, you have a linear classifier, and before that linear classifier, you just did lots of processing with that convolutional layers. What is that? Any idea we had in the course which does the same thing? You first just process your data, you get a kind of, maybe high dimensional features, and then you do linear classification on that. That was? Not PCA, no, be careful. It was about supervised learning. What was the first nonlinear model we had? support vector machines, right? You remember support vector machines? And what did the support vector machine do? It gets your data, the input here, and then it's going to just do some embedding on that, right? That phi function. It's going to compute some embedded feature, right? And then you get that embedded feature, you do linear classification, right? So this convolutional neural network, again, it is essentially one SVM, right? This is why when I started, I told you SVM is like the most general form of all of these neural networks. Because essentially what you're doing by convolution, you're just trying to find the right embedding, right? The whole thing that you are doing by convolution, you are just doing convolution after convolution after convolution to end up with a bunch of features. And then you read all of these features as a kind of big vector. This is your embedding. And now you are doing linear classification on that, right? So again, this guy is representational learning. And you're learning that representation, that embedding using a convolutional neural network. It turns out that for learning the representation of images, the best thing you can think of is, again, convolutional neural network because it's a deep model. It can get trained properly and so on. Yeah? But you should not think that this is totally new thing. It's, again, SVM. It's, again, the feed-forward neural network. The only difference is that you're now doing all of those representations instead of weird polynomial kernel or instead of using a fully connected neural network. You're doing it with convolution, right? But it doesn't change the fact that you're doing SVM, right? Everybody's clear? Questions? So you feel okay about the convolutional neural networks? Okay. So if you find it okay, then let's try one example. Oh, this is not very good. So, no, like, so I don't know if I can do. Okay, here I think, no, only today I forgot my pointer, so I had to do it on this computer. But anyways, so I'm going to read the numbers for you. I mean, some of you have computer already, so you can see it, but I'm going to read the numbers so that you get, if you cannot see it from there. So this example is the example of AlexNet. So anyone knows what is AlexNet? When was AlexNet introduced? 2012. Do you know where it was introduced? Here at UofT. Do you know what it did? It was the winner of the ImageNet challenge. So there was the whole idea of deep learning, or the whole belief on deep learning, started after AlexNet from UofT, which was done by a master's student and Professor Geoffrey Hinton from CS department here, could win the challenge of ImageNet. And the ImageNet challenge was that you have lots of images, the ImageNet data set, and you want to do image classification. It has 1,000 different classes. It's a very hard classification test, or it used to be, not nowadays, but it used to be a very hard classification task. And up to 2012, since the start of the challenge in 2010, nobody could win it. I mean, nobody even thought of using deep neural networks, because deep neural networks at that point of time were just fancy things not being able to be implemented and trained. So people use rule-based approaches, shallow approaches, simple things to just win. And they used to win and very happy and always look down to people doing deep learning till AlexNet could win it with a big margin in 2012. And this was the moment that people started to believe deep learning is going to work, right? So many people assume that this is the birth time of deep learning. So AlexNet was one of the first, say, serious models for deep learning, and it was a convolutional neural network. Now, if you look at this one, the input is a 3-channel image of size 220. Here is 227 by 227 because we do zero padding of size 3 by 3, but I mean the ImageNet is 224 by 224. Anyways, let's just work with this one. 227 by 227, 3 channels. So it means that you're going to have 3 different maps. Yeah? Every single of them has 227 by 227 different pixels, right? Now, you want to compute your first output. And when you look at your first output, so the first convolutional layer is that it does a convolution, what you see in between. So take this guy, see if it works. You see my mouse right now here, right? So this convolution here that you see, this is written 11 by 11, stride 4, and then 96 kernels. 96 kernels. Kernel is filter. Those filters, also people call it kernel. So 96 filters. Now, what's going to happen to your output? How many channels you are going to have at your output? Any idea? How many channels we're going to have? We are doing convolution, and in this convolutional layer, we are using 96 different filters. How many channels do we have at the output? 96 channels, exactly. So you're going to start from a 3-channel image, and then you end up with 96 channel image, right? So I told you that the input is 227 by 227. Just forget about that 7. That is the thing going up and down because of zero padding. Now the stride is 4, so say the input is 220 by 220. What's going to be the size of every single map at the output? So stride is 4, meaning that you're jumping with step 4 when you're just moving in the pooling. So the size of every single map is? What's going to happen to that 220 when I just do with the stride 4? It shrinks, right? What is the factor that it shrinks with? 4, right? So 220 divided by 4 is going to be 55, right? So the size of this guy at the output of your convolution is written here 55 by 55 by 96, right? Which is 55 by 55 is the size of every single map coming out of every single filter, and then 96 of them because you have 96 different filters, right? Everybody's clear? Yeah. Because the input is 220. 227, yes, but they don't do zero padding anything. So a bit of it goes with the fact that your filter is not going to your input and output are not exactly the same, right? So, for instance, if I have something like, we had it in the examples here, like you always have a bit of change, right? Oh no. Here, like here, or maybe, here. See, even if you do it with a stride 1, you're not going to exactly have here your 4 by 5, right? But the output is not exactly 4 by 5. It's 3 by 4, right? Because you start from here, right? And then this is the first one, second one, third one, fourth one. Then you don't have anywhere else to go, right? If you do zero padding, then you can go further out, right? But they have not done the zero padding, right? And then you have 11, and then when you don't do zero padding and you ignore it, those 7, being left, right? Yeah. But you don't need you can do the calculation by hand. It's not that complex. It's quite simple. But for now, you can always roughly talk about the input-output by the factor. So, yeah. So let's get here. So now, here, this guy. So now here you have 55 by 55 by 96. Now next time, what you are doing max pooling. And in the max pooling, you are doing it with filters of size 3 by 3. And you are doing a stride 2. So if you do a stride 2, what do you expect to happen to your map size? So from 55 to 55, it should drop to half of that roughly, which is 27 by 27 at the output. This is roughly the same thing. The number of channels, of course, does not change because you're doing pulling on every single channel, right? The same way. So nothing is going to change there. So now that you have this, you again have another convolutional layer. So you see my mouse here, right? So the convolutional layer, the next convolutional layer is 5 by 5, and then it has 256 different kernels, different filters. So what's going to be the size of output? What is the number of channels at the output? Number of channels is 256, because you have 256 different filters. Each of them is computing one channel for you, so you're going to have this much channels at the output. Then the stride here is 1, so nothing is going to change. And then because of that, you have 27 by 27 input, and then you again have 27 by 27 output. Clear? Now, one question. So I told you here in this layer that you have 256 different filters, right? What is the size of every single of those filters? So it says that the filter is 5 by 5, but does it mean that your filter is just a two-dimensional map, 5 by 5? No, it's 5 by 5 by 96. Great. So it's going to have 96 different channels because your input has 96 different channels, right? So this is why in this diagram you see that you have this, big filter. You see inside the input you have this, very deep filter because the number of channels is the same. So again, it does a max pooling with a stride 2, which is roughly making everything half. So now you have 13 by 13, 256. And again, you do another convolution. In this convolution, you're going to use 84 different filters, which going to give you an output with 384 different channels, right? Another convolution, again, you get same number of channels at the number of filters that you have. And then finally, when you are here, after doing the pooling, you're going to end up with this tensor here that you see. So this guy. So in this one, what you have 256 different channels. And every single channel, after doing all of these convolution poolings and downsamplings, you ended up with having every single map being a 6 by 6 map, right? So every single guy is 6 by 6, then you have 256 of them, right? Okay? And now this is the moment that you do the flattening. So if you do the flattening, how many input do you have? It's going to be 6 times 6 times 256, right? So this much, 36 times 256, you just go ahead and compute. I guess this 9,216 is that value. And then you are going to have two hidden layers fully connected. So this 9,260 is going to just map into 4,096 different features, again mapped to another 4,096 features, and then finally you're going to get 1,000 outputs which are activated by softmax. So you're going to get a vector of size 1,000. Every single body in that is a probability, and if you want to find out what is the class, you're going to select the one which has the highest probability. Yes? They just tried. Yeah. By the way, nowadays we know that this is not the best way you can allocate your channels. Like for instance, they go for very high channel, which is 384, right? 384, and then they drop to 256, which is not anymore the case. We don't do it. But you should give it to them because at that point of time, they were the first people doing it, right? But after that, like the year after someone else came, and then he could essentially improve the hyperparameters. But at that point of time, they didn't have any clue. They only had the clue that convolution is good because LeCun has said that in Lenet. So they just wanted to try it. And why they did it so deep? Because they believed on deep learning. They believed that if they go deep and if they implement everything perfectly, then it's going to work.
So they just like trial and error, you just try it.
They have some intuition based on the visual properties of the images behind the scenes. So they knew that this idea that you should go for smaller feature maps and larger number of them, this is something coming intuitively from the visual interpretation. Because at the end of the day, I have it in the next slides. So at the end of the day, what you want to do, you want to look at this image and you want to find out, for instance, if it is classifying an animal. So there are some features inside that which is going to tell you what kind of animal that is. And that is, for instance, the eyes, the beak, the snout if it has. Depending on those stuff, you're going to just cancel out some cases. If it has a beak, it's not a pig, right? So now you want to have those features, right? These are the features that you want to extract. And essentially, all of those channels, somehow you can see that. I mean, if you play around with convolution a lot, you're going to see that each of those channels at the output of your convolutional layer is somehow grasping one of them. And you really don't need to have a very huge map to just focus on a beak. But at the same time, you need to have a lot of these channels because every single image contains so many features, right? Yeah, so this was the idea, and they somehow developed it into this computational form. But of course, they spent lots of time on that.
Are there like principles at play? It's weird because like we have tools like stride, max pooling, and then looking the amount of channels as well.
Yeah.
Like, is there a principle behind each of them that dictates like when you should do more, increase your stride and so forth, or is it all just based on sheer intuition?
It's not based on intuition only. I mean, like as I said, like those people who have worked. Like, for instance, do you know about this idea of waveform transform of an image or Fourier transform? Yeah. So this comes essentially from the same thing because people do know that this image is very high frequency, right? But even if it is very high frequency, you essentially have a lot of harmonics, and every single of them has just a few components, very sparse, right? So this, like from the frequency domain study of images, you get a bit of understanding how you can do it. Okay? But this is only a story 2012. Nowadays, nobody think about that anymore. Because you essentially, all of these numbers, I mean, you want to do visual tasks, like there are billions of models out there. And if you look at all of them, you're going to see the pattern, how they design it, and you can come up with your own design. This is not a big thing anymore. So, questions? For ImageNet is 224 by 224, but they are doing zero padding here. So they just add a bit of zero around it. Yes?
For the fully connected neural network,
yes.
Why is it 4096?
Yeah, I mean, again, they just chose this hyperparameter, this size. No, I mean, at the output here, you have 9,000 something, right? 9,216, I guess. So that is the number of features you have. And I mean, probably the main limit at that point of time was their computational power, right? They couldn't make it larger, probably. But as I said, this is not the best design you can think of. You can do much better, and a lot of better architectures came after this. This was only the first one which worked. And so this is not very optimized, definitely. Yeah. Yeah. Questions? No question? Great. So if you got no question, then let's just do one custom CNN together for MNIST classification. So you remember MNIST classification, right? We talked about it before, or no? So do you know what is MNIST data set? So the MNIST data set is the data set of handwritten digits. And the handwritten digits are like 0, 1 till 9. So 10 different classes, okay? And then it has 70K different samples in it. 10K usually reserved for tests. 60K are used to train, okay? And if you want, you can again split it into validation and training set, right? And the number of digits within the data set is the same for all the digits, meaning that from this 70K, 7K are handwritten 0, 7K are handwritten 1, and so on. So students at this school wrote handwritten digits. People took the images. They have been saved in 27 by 27 pixel, and they are gray images, so they have one channel only. And this is one of the most basic data sets that we have because the classification is simply 10 class classification. It's a very simple thing. And the data set, first of all, is 28 by 28. It's nothing. So you can simply do it with a fully connected neural network easily. This is the first thing. And the second thing is that the data itself is not very complex, right? So it's just a white background, one handwritten digit, which is not a complicated thing at all, right? So you even can do it fairly fine by logistic regression. But this used to be a kind of toy example for many, many studies because this is easy to implement and check. And if you want to do it, so you see here we have one MNIST image. And this MNIST image is 28 by 28, as I said. Okay? So this is your input. You have one single channel. And now you are just doing convolution. And when you do convolution, if you use 10 different filters, then you're going to get 10 different channels at the output. Okay? And now here I'm doing it with stride 1, meaning that this 28 by 28 should not change that much. So at the output we have 24 by 24, and that is simply because the filter is 5 by 5. So when it starts at the first column, it's going to end up at the column 24, right? And then it cannot go after that because I'm not adding any 0 after that, right? So my filter is going to stick to the right-hand side. So the output is 24 by 24, 10 different channels now, right? And then again, what I'm going to do, I'm going to do 10 other filters. And then, first of all, I am doing max pooling 2 by 2. And when I'm doing max pooling, I do it by a stride 2. Meaning that I get from 24 by 24 here to 12 by 12 here. So I have now 10 different channels. Every single channel has 12 by 12 pixels maps, right? And then I can do another convolution again, right? 12 by 12, I do 5 by 5 kernels, 5 by 5 filters, and I don't use any stride here, so stride is 1. And I use 20 different filters. This means that I'm going to get at the output 20 different channels. Now every single channel is 8 by 8 because, again, I'm not doing zero padding, right? Okay? Clear? Now, these filters that I have here, 20 of them, what is the number of channels for every single filter? You look at the number of channels of the input, right? Which is 10 in this case, right? So this means that I have 20 filters. I write here down 5 by 5 filter, but 5 by 5 filter is actually 10 channel filter, right? So the very accurate expression is 5 by 5 by 10 filter, right? And I have 20 of them. And now when I have 20 of them, I'm going to get this 20. Again, I do pooling with a stride 2. So I'm going to end up with 20 different channels, each of them being 4 by 4. Now I am doing just flattening. So here I think it's quite easy for you to compute. It's going to be 4 by 4 is 16 times 20. It's going to be 320 different values, right? So then you're going to get all of these 320 different features. You put them in form of a vector, and then you connect it to one fully connected layer, right? So say, for instance, I am getting this 321, so I'm going to put all of them here, and then I am just computing 10 different classes. So essentially, I'm just doing a linear regression here. And this is the single fully connected layer that I have here, which is connecting 320 features as the input that I have to 10 different outputs. And I just activate them by softmax. Then I'm going to have a probability vector. Again, I select the one which is maximum, right? Everybody's clear? Yeah.
What do you mean by a 5x5 kernel? I know on the last slide when we said kernels and filters, we use switch maps interchangeably.
Filters and kernels, yeah, it's the same thing. It's the same, as filter, right? By 5 by 5 means that that window that you are moving, the size of that one is 5 by 5.
Oh.
And then the number of channels is exactly the number of channels at your input. Okay? Yeah. Sorry? 10 channels to 20, I just chose this because I used 20 different filters. But each filter has 10 different channels, of course. So I have 20 of these very, deep, very high depth filters. Questions? So everybody's clear? Yeah.
So we're saying that by using the pooling, we are making data smoother, right?
Yes.
But with the stride larger than 2, would it have larger than 1?
Yeah, actually this is the reason that we do it first. So we do pooling and then we do stride large, right? Larger than 1. Then when you do pooling, then this is going to somehow smoothen your map. And then now that you drop a few things, you somehow captured all the information, right? So this is going to help you maintain features more. So if you do pooling and then you do the stride. Okay? Because if I don't do any pooling first, okay? When I do the stride, it means that stride is essentially like downsampling. And this means that when I start from the first window, then I jump to the next window. And there are a bunch of numbers here being missed, right? But when you do first pooling, then for instance, you compute the average of all the values, right? So this average is going to somehow expand over your map, right? Now if you jump, it's true that you're missing some values in between. But when you jump from one to another, the other is already having a bit of those features which you're missing, right? So this is one of the key reasons that we always do pooling and stride together, the downsampling. Because if we just do it before that, so this is one other point that this guy is not a very conventional anymore. Because at the very beginning, they are doing a stride. Which probably at that point of time, they somehow were convinced that this is a good idea. Maybe they just wanted to get, smaller filters, smaller feature maps. But this is not the typical one. So nowadays, if you want to do it, we do it with a stride 1. Then we just do pooling and do the downsampling. Yeah. But this is a good point. Yeah. Okay. Questions? No question? Okay, great. So if you got no question, so let me just quickly finish this part and then we're going to have a short break. So one thing about the training of convolutional neural network, of course, if you want to do training, this means that you should go back and do backpropagation, right? You just do forward pass, you just put your image at the input, you compute all those output maps, right? And then once you computed all the output maps, then you're going to go for the fully connected layer, you compute every single neuron there, you compute your output, now you're able to compute your loss, right? For instance, the cross entropy between the output and the true label, right? And now you need to move all the way backward to the beginning of the convolution, right? To your image. And you need to just compute all of these partial derivatives right after each other till you get to that input, and then you get one single sample gradient, right? Now, I'm not covering it here, but in the deep learning course, we have it. So you can see that, exactly like the fully connected layers, that backward propagation or backward pass is basically the dual thing of the forward pass. So here, linear operation and backward activation and so on. Again, you can see that when you are moving backward in the convolutional layer, that behaves again like a convolution. So once you have like the gradient of the output and you want to compute the gradient of the input, it's essentially again one convolution. So you do convolve it with the filter, and then you get the backward, the gradient of the previous layer, and you keep on going towards very input. And once you have it, so you have that sample gradient. Of course, you need to do it for multiple samples till you have your whole mini batch computed. Then you average them. This is your gradient. Now you can do one step of gradient descent. This is the idea of SGD, right? So same thing as we did for fully connected networks. You can apply it here. And if you're interested, you can try it once, like for a simple convolutional layer, and see how it looks like. Questions? Everybody's happy with CNN? Not the news agent, like not the CNN channel, this CNN. Okay, so one thing that I would like to just emphasize here is the idea of like feature extraction. And I somehow tried to explain it for you through the CNN or convolutional process in the AlexNet and or custom CNN. What is happening inside convolutional neural network is that you typically start with your input, and this input essentially is usually a very big input, few features, right? A few channels, right? And then the thing that you are going to do, you're going to do convolution after convolution and after convolution. And the initial convolutions are essentially checking the low-level features of your image. They're just going very carefully over your image, step by step, looking into it, compute something at the from that, and then they write it down at the output map, right? Once you do that, you do the pulling, and then you just drop a bit of that. Again, you keep on doing this, right? And then gradually, your features are going to get processed into mid-level features. Meaning that when you start from the image, you're going to get a bunch of, like, this is the heat map that you have in every layer. And then, for instance, the first layer, the first channels, the channels in the first layer are just showing you a bunch of images which are totally nonsense to you because they are actually grasping the low level, how the edges are changing, for instance, in the image, right? But gradually, when you keep on doing the convolution, you get into mid-level ones, which somehow looks like if it's image of a human being, then it's going to look like how is ear is somehow getting into one channel, the nose is getting into another channel, eyes into another channel, and so on, right? And then when you get to the very, very end, you're going to get into the very high-level features. And these things that you see here, these are just presented for some images over neural network. Like you are looking at the CNN in the middle, and then you assume that those feature maps are images. Again, you plot them, and you're going to see such a behavior. Like towards very end is like very high-level versions of the features. Like the face is looking like an, 20-year-old man from front. From this side is like 30-year-old man. From this side is like, 26-year-old woman. From this side, it's looking like a kid. So it's like generating lots of high-level features, right? And when you have those high-level features, they are essentially something simple to be converted to the class, right? Because you want to find out what is the age, for example, the age and gender of the owner of this image, for instance, right? Once you have this kind of high-level features, then it is easier for you to decide, right? So most of the features I see are telling me that it's a man and it's between 20 to 25. So I'm going to guess it's a man, roughly 23, right? This is easier as compared to starting with the very low-level features, because the low-level features are a bunch of edges, right? What is the edge of this ear with the background, right? And you don't understand anything from that. You see? So this is the whole process that is happening by convolutional neural network, but of course, this is only happening computationally. So you don't really find out what is the exact function doing this for you. You're just training the convolutional layers, and then those convolutional layers, because of the universal approximation theorem we talked about before, they are going to somehow approximate the right transform to show you the features that you want. Everybody's clear? Questions? Okay, so if you got no question, just one last note here. So nowadays, if you want to use CNNs, I mean, you can use AlexNet, you can use VGG, for instance, one of the latest CNNs proposed in 2014, which was somehow competitive, and it again won ImageNet. But at the end of the day, you cannot simply just use a very, very deep CNN, and, or any deep feed-forward neural network. And one of the key reasons is the issue that we call it exploding or vanishing gradient. Vanishing is the thing that happens more and more in practice. And that means that if you have a neural network, you start from the first layers and you keep on going deep into depth. When you are at the very output, once you want to do backpropagation and compute the gradient, you start with the gradient here and just move backward, right? And each time you move backward, by chain rule, you're somehow doing lots of multiplications, right? And those multiplications, if you start with the small values, which are usually the case because all of the activations, all of the loss function, everything that you have are giving you small derivatives, this is going to get smaller and smaller and smaller, right? And if you just write down backpropagation in details, you're going to see that all the weights, for instance, that are in this layer are going to be updated with the derivatives backpropagated up to this point. Okay? This means that the weights in the initial layers are not going to get updated very good because they have very small gradient, right? This is the behavior, we call it vanishing gradient. And if you just implement a very deep feed-forward convolutional neural network, then you're going to see that at some point when depth is increased, your model is not going to improve in performance, and at some point you're going to even perform worse. Okay? This is simply because there is no gradient arriving anymore at the input layers, like the early layers. And this means that the low-level features you are extracting are not good enough, so you're going to get bad low-level features, and this is going to somehow propagate all over the network towards the end, so you are going to have poor conclusion at the very end. Everybody's clear? So this is the property that we call it vanishing gradient. Many people came around with different solutions. The very well-known solution is the idea of skip connection, which is nowadays being used in ResNet, residual network. And residual network now can be super deep, right? ResNet 134 is a typical thing. 154 is a typical thing. ResNet 1001 is there. I mean, not everybody uses that, but it's there. And the whole idea of a skip connection is that you just don't go simply in depth, right? You just don't put every layer after the other. You can somehow just skip a couple of layers as well. So you just connect them, and then once upon a time you get one output of one layer, and you skip a couple of layers, and you add it up to the output, right? So these red connections are what we call them skip connection. Most of the architectures nowadays you see for visual tasks, very sophisticated and working fine. Like as I told you, ResNet, they're all using a skip connection. DenseNet is using a skip connection. UNet is using a skip connection. All of them use a skip connection to get rid of the issue of vanishing gradient. If you don't do that, then you're going to vanishing gradients. And there is the original paper introducing ResNet. It has explained why it's working fine. You can mathematically show. I mean, if you write down the backpropagation for this architecture, you can see that the vanishing gradient behavior is not happening anymore. Okay? So this is also good to have to be heard, right? So if you one day need to work with ResNet, it's not a complicated thing. It's essentially CNN with a bunch of skip connections. So If you're in, I mean, chapter 9 of Goodfellow, it has the basics of CNN. So if you want to read ResNet or more like advanced things, you need to start looking into papers, like technical papers or implementations or other notes. So they are not anymore like in these textbooks that you have. Yeah, and we have it also in the deep learning course. So in the deep learning, applied deep learning course, there is a chapter about this stuff, so we get a bit more detailed into this stuff. So any questions? So if you got no question, let's have just 5 minutes break, and then we just start with this part, which I try to just be very brief. I'm not sure. I mean, it was supposed that it should be available tomorrow morning. Oh. Yeah, but I guess like this grad is just a bit behind the schedule. They might do it like in 1 or 2. Oh, they might just bring it out later, right? Yes, yes. But I mean, if everything works fine, you should do it tomorrow. But I know that they just wrote me they sorry for the big deal. Oh, okay. It might be late, but it's no problem. Is it happening? Do you know what time it's going to be happening? Oh, they haven't fixed the time, but I told them no. I told them that they are going to do it. Oh, okay. But you're going to get it like at the capital. It's not there. Not there right now. Yes. So you're going to get posted. Since it's the first semester, they might consider it. Okay. Right, thank you. So, shall we go on? So, what what we studied up to this point, it was all about dealing with feed-forward networks. Or if we want to talk in general, we were always talking about IID simple data sets. And the data sets that we had up to this point, they were all including IID samples. Or, I mean, even if they are not, we just assume that, right? Meaning that we assume that every single data that we have in our data set is corresponding to one label, right? There's one image, it's classified as dog. There is one, I don't know, number or weight is corresponding to one person, or it's not one specific bunch of properties describing one particular object, right? And then all the samples that you have inside your data set, you assume that they are independent samples, right? So multiple images, each of them has its own independent label. And you use that to just train what we call it a feed-forward model, right? Meaning that your model is going to get your input and gives you another output. Then you go for another input, and then you see the output, corresponding output. You are able then to compute the empirical risk. You are able to train it. And you can do something like one-shot learning tasks, right? So one-shot input, one single input goes inside. And then you look at the whole input at once, and you give your output, your conclusion from that input just at once, right? So this is the idea of IID data set, or the principle of having IID data set with one-shot learning tasks. But in practice, most interesting applications that we have deal with sequence data, right? For instance, like speech writing, right? So you have audio and you want to have the text for it. So that audio is not essentially a simple one giant thing going, and the sentence is not one single label coming out, right? It's a sequence of parts, right? So a sequence of, for example, 3-second audios, and then you want to look at every 3-second audio, and you want to generate the corresponding text. And not necessarily all of these 3 seconds include the text that you want, like the complete part of the text, a complete part of a word, or a complete sentence, right? So you have such example, or for instance, you have a music, and this music is going to just go on, the whole notes are going on, and then you want to look at these notes, or hear to these notes, and at some point you conclude what is the genre of this music, right? Or other examples, for instance, you want to look at the comments on Amazon for one product, and you want to conclude whether this is a good product or not, right? So you want to find out how good the comments are. And again, the comments are sequences, right? A sequence of long text, and they're going to have lots of weird, expressions inside them. And you need to look at this whole sequence together, and then you are able to just give an argument at the end. And other examples are, for instance, when you want to do captioning. So you have one image, and then you want to write down one caption for that image. That caption is again a sequence, right? The first word, the second word is depending on the first word. The third word depends on the 2 previous words, and so on, right? So again, you're dealing with a kind of sequence here. Or, for instance, when you want to classify a video, right? So the video, you don't look at the single frame of it, right? It's a sequence of frames, and these sequences are depending on each other, right? And now you want to look at this whole sequence, and then at some point say that, okay, up to this point, it was showing something about sport. Now it just switched to some movie or so on, right? So in practice, most of the applications that you deal with are dealing with some sort of sequence data. And the whole question is that how we can fit what we have learned up to this point to these sequence data. So with these, for instance, feed-forward neural networks, and by feed-forward I simply mean fully connected or convolutional neural network, doesn't matter. These kind of models that get one input gives us one output, how we can use them to just make sequences with them, right? Or process sequences with them. And the key point about the sequences is that these sequences are not anymore a sequence of independent things, right? So they are a sequence of different frames, for instance, different features, different samples that are relying on each other. So they have temporal correlation, right? When I say a sentence, this sentence, of course, it's not simply independent throw of words, right? So when I say one word, then the next word is somehow depending on my previous word, right? And so on. Everybody's clear? So this is the idea, the problem of sequence learning. So in sequence learning problems, you usually have the input or output, or sometimes both of them, to be a sequence, and you need to be able to somehow deal with these sequences. So if you want to think about it in a very general form, then you could say, okay, a sequence learning problem is that I have a sequence input, and now I want to learn a sequence output. And if my input or output, any of them, is just one single thing, then it's going to be a sequence of length 1, right? For instance, here in this image captioning example, so your input is just one single image, but again, I can think of one single image to be a sequence of length 1, right? So you can talk about the general problem where you have a sequence input, sequence output, and how you can deal with them. Well, there are different approaches, basically developed through time. So the first wave was recurrent neural networks, which I tried to just briefly explain today. So the idea was that you get your basic MLP or CNN, and you try to somehow add the property of recurring to it so that you start to work with sequences, all right? So this was the most basic one. The most successful model we used for that, you might have heard of it, was LSTM, right? Long short-term memory model. But they are somehow limited in their power. The more powerful architecture is, or solution is the idea of encoding, decoding, or what we call it sec-to-sec model, sequence-to-sequence model. So this is a more sophisticated version, which is again made based on RNN and CNN and those things, but with a more sophistication. And the last one is the idea of transformer. When people started to somehow improve those approaches, they ended up with a mechanism called attention, and that attention somehow ended us up with transformer. Okay? So these are the three key approaches nowadays being used. Probably you know that most of the LLMs nowadays you use are transformers. So GPT is, what is G standing for? General pre-trained transformer, right? So, yeah, it's a transformer. It's the last guy, right? So everything that you have in these chatbots nowadays, these LLMs you use, they are all transformers. And somehow they went through this development here. So now let's just look at the sequence problems. Let's get a bit familiar with what is the sequence problem, and then we get a bit of flavor of RNN. So in sequence problem, you can have different types of problems. For instance, you could have one-to-many problems. So you can have one sequence of length 1 as the input. So one guy goes in, and then you want at the output to have a sequence, right? So that sequence is, one example of it is your image captioning problem, right? You give one image as the input, and now you want to have one sequence at the output, the sentence, right? The caption. This is one case. The other case is the other way around, so many to one case. So it means that you get the whole sequence, for instance, the whole note of the music, and then at the end you want to classify what the music is, right? So your input is now a complete sequence, your output is just one single output, which again you can think of it as a sequence of length 1, right? And you could have many-to-many problems. And many-to-many problems, for instance, it could be the one which I have on the bottom left. So this is after every, so you have one sequence as the input, and at every single time you want to have, in this sequence, you want to have one corresponding output, right? So this is like I have a sentence, and for every single word inside the sentence, I can give a syntax, right? So if I want to label, to tag every single word inside the sentence, then it's a syntaxing problem, and this is many-to-many with every single entry inside this sequence having one corresponding output or label. The problem could be of the form top right, as you can see. So you have a long sequence as the input. You have your output is starting at some time later, for instance, right? For example, it could be translation. So you are saying one long sentence in one language, and like, for instance, you're talking in German, so you just need to wait till the sentence is over so you know what is the verb, and now you can write down the translation in English, right? So your input and output both are sequenced. They are both having many different entries inside them, but they are not perfectly aligned in time, right? So this is another kind of problem you could have. Or you could have something like the last one, so the one on the right down. So that one has like output after some time, right? Once upon a time. For instance, you're just listening or watching a video. You have the sequence of, the video is the input sequence, and you want to just segment it into the parts, right? So the first part is talking about chapter 1, the second part is talking about chapter 2, and so on. So at the end of every segment, you are going to give one tag, right? End of segment 1, end of segment 2. So again, you have one sequence input, one sequence output, but the sequences are neither of the same length nor exactly aligned, right? So this is different kind of problems that you could have, and essentially what we did with this feed-forward neural networks was one-to-one problem. So you have one input, one output. So you were just doing one very, very specific case of all of these, various kind of problems that you could have. But the key point about that is that once you can do that one-to-one problem, then you can start develop models that also handle these situations as well. So now let's start with the idea of recurrent neural network. So what is the idea of recurrent neural network? The idea is that if I have one neural network which is connecting one input, for instance, X, to the output Y. So X is the input image, Y is the final classification that I have. Now, if I don't have only one image, and I have a sequence of images, now, and I want to have a sequence of outputs, now, how can I just modify this architecture to somehow uses the information of the previous time every time that it's just deciding on the new input, right? So the key idea that people started to think of was the idea of recurring, meaning that instead of having this architecture, you just do that architecture. So once you just get your first input in the sequence, first image, you get the output. But you know that that image is actually one frame of a video. So the next frame is going to be very correlated to that one, right? So your decision on the first frame is going to impact your decision on the next frame, right? So you're going to collect the features you computed in the first time instant, and again you feed it back to your neural network, right? So you're going to get H at time 1. H here is the bunch of features you computed. So you think of that a yellow box to be your, for instance, embedding, right? Like in SVM, or just hidden layers, all the hidden layers together, right? So now you can get those hidden features and again feed it back to your neural network in the next time. What is the benefit of that? Next time that your neural network is going to decide on the next frame, it already knows the features of the previous time, right? And then it's going to get a bunch of new features. Well, if you just go over time analysis and other things, you can show that the hidden values, the features that you're computing right now at every single time, these H values, they're going to somehow depend on everything before, right? And this is somehow carrying information towards futures. This is coming from the idea of state-dependent systems. And you can think of H, the hidden value, which is recurring now, as a kind of hidden state. We call it hidden state. So it's a kind of state of your neural network, saying that up to now how your neural network is feeling about the whole thing, right? And the next input comes, when it wants to talk about that, it also looks at its own state. How am I? And then it decides for this time, and then it updates its own state as well, right? Because the features also get updated through time, right? Everybody's clear? So this is the idea of recurrent neural network, and you can actually turn pretty much any architecture that we had up to this point, you can turn all of them into recurrent neural network. For instance, say we have a very shallow, basic feed-forward neural network, so your X is the input, then it passes through one hidden layer, you get the bunch of output H, and then you do one linear classification, you get your Y at the output, right? So this is just a simple, shallow neural network, correct? Now, how can I do recursion here? So let me just formulate everything. So say that my hidden state, hidden features, because we are still having F and N. So the hidden state, H value, is computed by a fully connected layer, right? So I had a fully connected layer, W1, getting multiplied to X, give me a bunch of features. I just activate them. This is my hidden feature, right? Now that I have this one, I do linear classification or regression on that one. So again, I get those features H. I just do one other linear classification or regression, linear transform. And then again, I activate it, right? So this is going to be my last output, right? So this is a basic thing, pretty much the first neural network we just tried, right? So XOR neural network, for instance, right? It's that one. Now, how I can make it to recur, to just do recursion? Well, I can do it this way. So, okay, I missed this slide in my mind. So here is just explaining how we can think of it. So here, your Y, the output, if you think of classification problem, is, for instance, the output of softmax, right? And this Y, which is coming out of softmax, is going to compute the chance that the label for your input X is something V, right? So for instance, if you have 10 classes like in MNIST, it's going to give you 10 probabilities, Y, right? Output of the softmax. And every single of them is the chance of this input that you have given to your neural network belongs to the corresponding class, right? So you can think of the output of this, feed-forward neural network computing the probabilities for you. And we talked about this. We can always do maximum likelihood on that one, which is going to end up with just using cross-entropy and minimizing that empirical risk, right? So that was what we did before. Now, we can just add recursion here as well, simply to this one. How I can do it, I can say that, okay, if I am at time t, so right now you don't think about the beginning of time, assume that I am somewhere in between, okay? I'm at time t. This means that I already have seen everything in the previous time, okay? Now, when I am at time t, when I want to compute my hidden features, I don't simply just get my input at that time, which is xt, and do the linear transform and activation. I also take into account the feature of the previous time, right? So I already have seen ht minus 1, the one which was in the previous time. I have it. This is my hidden state. I'm going to get that one back. I get my new input. I linearly transform everything, and then I activate, right? So this is going to be my current hidden state. And now I want to compute my output. I get this current hidden state. I give it to my linear layer, the next linear layer. And then this is going to linearly transform everything. I activate. I'm going to compute the output, right? So this is what I mean by recursion. It means that at every single time, I have something inside my neural network, essentially the output of all of them or bunch of those neurons in the hidden layers. And when I want to compute their next value in time, I use their previous value in time as well. And this is going to somehow do recursion for me, right? Everybody's clear? Questions? So now, if I do that, what does the output that YT is going to compute for me if I think in terms of classification, for instance? So if I didn't have recursion, we said that YT is going to just compute a bunch of probabilities of the labels given the input that I have, right? But now my input is not simply X. Look at this one here. So the input is not simply XT, it's XT as its hidden state of the previous time, right? So it means that it is computing the probability of my label at time t, Vt, right? The label that I have at this particular time, given whatever I have given to this neural network as input. And now the input is X and ht minus 1, right? My previous hidden state. But that previous hidden state was computed out of what? The input in the previous time, right? So it depends on that guy. And the previous hidden state, right? What was ht minus 2 computed based on? ht minus 3 and xt minus 2. So it depends on xt minus 2 and previous one. And I keep on going backward in time, right? So this ht minus 1 is not only depending on xt minus 1. It depends on xt minus 1, xt minus 2, xt minus 3, and so on till beginning of time, right? So what I can essentially say, that I am right now computing the probability of my label given whatever was coming to my neural network up to this point, right? So now you are just adding a time dependency to your neural network, right? Now it can handle a sequence. It can learn from a sequence, meaning that when it talks about the label Vt, it's not only looking at the input at time t, it's looking from all the inputs from the beginning of time up to this point. Everybody's clear? Questions? No question? Great. So this is essentially RNN, and you can make RNN with any neural network that you already have learned, right? So if you get this shallow MLP and you just do this recursion, then it is going to be basic RNN. You can get a convolutional neural network. You do recursion wherever you want. So maybe you take the output of one of the convolutional layers. You just inject it back to the input. And then this is going to be your own convolutional recurrent neural network, right? So you can always do this recurring property happening. And then you depend your output at every single time to the time. And then this is going to be a sequence model. So a sequence learning model. Now, if you want to just see how it's really happening in practice, so how it's, or you just want to develop intuition of how time evolution is happening in this neural network, you have your neural network. And everything inside your neural network is fixed, meaning that all of those weights you're using in all the layers, they're all fixed, right? Now, this neural network gets the first input. Maybe you just decide on one initial hidden state, right? Just randomly generate some hidden state. And this is the initial one. Now you are going to compute y1, which is essentially depending on x1. But then you go for the next time. In the next time, you're going to get x2. But in addition to x2, you're going to use whatever you had computed in the previous time, right? It's going to be h1, right? And then you get this h1 to your neural network. You compute your output again, right? Now this y2 is going to depend on x2, and h1, which depends on x1. So it depends essentially on x2 and x1, right? And you can keep on going like this in time. At every single time, like for instance, you compute this at t minus 1, then at time t, you are going to just compute, get this ht minus 1, you give it to your neural network back, you give the new input, and you compute yt, which is going to depend on everything up to time t, right? xt minus 1, xt minus 2, and so on till x1, right? So your output is now going to be a sequence. For instance, it could be a sentence, right? So every single time, you just generate one word in the sentence, and then whatever that word is, you just inject it back to your neural network. Then the next word that the neural network is going to say is depending on the previous words, right? Meaning that it's not going to give you random words anymore. It's just going to give you a coherent sentence, right? Yeah.
What would you put as H of 0?
H of 0, I mean, typically we just fix it to something. Yeah, like all 0 or something random, but you can essentially treat it as a weight and learn it as well. So that's also possible. So, questions? So you got the idea of recurrent neural network? Great. So you can keep on doing this, and maybe once upon a time you have one particular label. For instance, at Y2 you have your first label. So at Y2 is the point where you're going to segment your sequence, for instance. Then this is end of the segment, second end of the segment, and so on. So you can do that as well. So now, if you want to think about a generic recurrent neural network, as I told you, you can put here instead of HD any architecture, right? You can use CNN, you can use MLP, you can just use ResNet with a skip connection. You can use anything. As long as you have this recursion through time, then you are going to generate some sequence. So that's it. Now, the key issue with RNNs, which stop people from working with them, is the issue of training them. So what was the problem? Like RNN was somehow started somehow quite even earlier than many feed-forward neural networks. Like, I mean, linear classification and shallow networks were there, but many people started to work on RNNs as well because, I mean, it's interesting, right? So if you can generate a sequence, you can make people one machine to talk. This is very interesting problem, right? So many people were just attracted to this problem for a very long time in different communities, in different scientific communities. So this was a quite old problem, but people somehow concluded we cannot do anything about that. And the main reason is because of the training issue. And what is the training issue? I mean, I don't expect that you see it immediately here because it requires that you practice a couple of times the backpropagation to somehow see that how it's going to go backward. But I just try to intuitively explain how it happens if you want to do the training. So if you want to do the training, what you're going to do? You're going to get your input x1 to xt, right? So you're going to give that input, and then at every single time you're getting one output y, right? And then assume that you have for every single time one label, right? So for example, you want your neural network to make a kind of right sentence. Now the output that you see at the output of the neural network is at the moment something nonsense, right? Like he am you, right? This is the sentence that's giving, so you don't accept it, but you have label, like you put the label to be he is good, right? And now you want to make it to just change, so you have the labels, you have the outputs, you are going to compute the loss, right? So at the end of the day, this loss that you are computing, this R hat that I'm showing here, is going to depend to all of them, right? Depend on all of these outputs, right? Now, let's think about the very last guy here. Now, if you want to do backpropagation, what you're going to do, you're going to use chain rule. And when you use chain rule, you start with just computing partial derivative of that output with respect to, or the R hat with respect to output, and then you start to come down, right? So you get from the output down to the hidden features, right? But now when you get to the hidden features are not only depending on your input, they also depend on the hidden feature of the previous time, right? Correct? So if you want to just do a very complete and clean backpropagation, you start to just go backward in time now, right? Because your ht minus 1 is also involved there, right? And that ht minus 1 is depending on the weights that you want to train, so this is going to be included in the chain rule, right? ht minus 1, again you want to compute the chain rule, you need again to take into account ht minus 2, right? So if you just write down the backpropagation of one simple RNN, you're going to see that you always need to go backward till you get to the very, very beginning of time. And once you get to the beginning of time, since that guy is the one which is not depending on anything else, this is the moment that you are going to stop. So as I said, I don't expect that you see immediately the chain rule in mind, but just take it from my side. You need to just move backward in time. Okay? And if you just try it at home once, you're going to see for one simple example, this is really the case. Okay? Now, if you need to go backward in time, I mean, even if the network is very shallow, so you're not going very deep in depth, still you can have a very, very long sequence, right? So this means that your architecture in time is super deep, right? And now, if you just do lots of backpropagations, what could happen? I mean, we had it in a couple of previous slides. What's going to happen to the gradient? They can vanish, right? So they can vanish. And actually, vanishing gradient was first seen in RNN because people did not go very deep in depth initially. They were always working with shallow neural networks. But it's easy to go very deep with RNNs, right? Because the sequence could be long in time. So they started to see vanishing gradient happening in RNN, and because essentially backpropagation through time, when you do it, this is going to be similar to the backpropagation over a very deep neural network whose depth is in time now. Okay, so they started to see the same issues like exploding gradient or vanishing gradient, but this time you cannot simply get rid of that because I mean in feed-forward neural network you don't really go that deep initially, but even if you want to do it with one single hidden layer, one shallow neural network, still you're seeing that, and this is an issue. So people started to somehow mainly focus on this vanishing gradient because this was the very or more challenging issue. So the point here was that when you see the gradient vanishing through time, this means that when you are just training your model, you are having some gradients of the current time and a bit of future, but you don't have any gradient from far before, right? So the gradient of the very, very long time ago is very, very small. And this is going to contribute in your gradient descent very minorly, which means that somehow your neural network starts to forget whatever has happened before. So it's true that theoretically, by doing that recursion, you're putting the dependence there. But the problem is that when you are training it by gradient descent, this backpropagation through time and the vanishing of the gradient is going to limit your memory. And it turns out that your memory could be very, very small. Yeah? So now you have a very long sequence. You have a long sentence, and you want to find out what was inside the sentence. But even if you try your best and you train it as much as you could with the best algorithms ever, but at the end of the day, your neural network is only capable of memorizing a bunch of words, right? It cannot go all the way to the beginning of the page, for instance. Okay? So this was the issue that happened to these neural networks. They had extremely limited memory, and this is when people started to say, okay, forget about it. This is just a fantasy, right? It's not going to work, right? But through time, of course, people started to develop other approaches. Somehow some people didn't give up, and there were algorithms, like basic algorithms, clipping of gradients. You might hear it because it especially happens when you have explosion in the gradient. If the gradient is getting hugely large, then you can clip it, right? You could say, okay, if it's more than 5, then I treat it as 5. I don't increase it anymore. This is the clipping gradient, or truncated backpropagation through time, so you don't just go all over to the end, and then you just move backward to the beginning of time. You just go a bit forward, move backward, and then again you go a bit forward, backward, and so on, right? And then once you just go a couple of time instants, then you're not missing, you don't have a very long time, right? And then you're not missing too much there, so you keep that memory, you somehow carry it out through time. But again, this is not going to be a very sophisticated solution. The most sophisticated solution, which made a kind of breakthrough, was the idea of gating. Okay? And to be honest, I don't expect that if I explain the gating in details for you right now, within very short introduction, you're going to get it completely. So I don't want to confuse you too much. I'm just going to show you the architecture of like LSTM and GRU, just to break this taboo in your head that there is nothing specific there. So it's a bunch of calculations again. But this gating somehow is going to help us carry information over time for a longer period of time. So for instance, the basic architecture that we had up to this point talking about was that you get the hidden state of your neural network, whatever that is, and then you are going to combine it with your input X, and then you just activate it, typically with 10H, because 10H turns out to be better, or just vanishing later in time, and then you get your new hidden state, right? So this was the basic shallow RNN that I started with, right? So I got this H, I just multiply it to some weight, Wm. I got X, multiply it again with some weight, W1 say. I just added them up and activated them, right? This was my next hidden state, right? But you could also have other architecture which are what we call them gated architecture. So the most basic one is what we call the GRU, gated recurrent unit. So how does this one compute or update the hidden state? It basically does some operations which we call them gating. And gating essentially is just like a linear layer being activated by a sigmoid function. And why we call it gate? Because sigmoid is somewhere between 0 and 1, right? So it's like a tap of tap water, right? Water tap. So if you just put it 1, it's like you open the whole gate. If you just put it 0, it's like you close the whole gate, right? So this is the idea coming after the naming. And essentially, you can break down any gated architecture into like gates and linear combinations. For instance, here, you have one gate. So one gate is the update gate. It's essentially one linear layer activated by sigmoid. Again, you have one thing else, which is reset gate. Again, one other linear layer activated by some sigmoid. So these are gates, and now you are going to just multiply those gates with corresponding. So you first gate your previous hidden states, and now your previous hidden state could be multiplied with something between 0 and 1. If you let the gate to be completely open, then the previous hidden state is going to pass completely through. If you put the gate to be 0, you just block the gate, right? So nothing is going to come from the previous time. And you get the input, now you compute some output here, and again you use your next hidden gate to somehow gate this other guy again, right? So this is the idea of GRU, the architecture of GRU. As I said, I totally understand that you don't get what gating is right now. This is not the purpose of this lecture, because this is just an overview, right? So if you want to understand it, this is a part of deep learning. So you need more background to be able to digest all of it. It's just to break the taboo in your head. So if you want to just implement, I mean, even if you don't attend this lecture, as long as you feel self-confident, you can look at this formula, you can simply implement that. I'm pretty sure, right? So the whole purpose of these lectures is to just give you understanding, right? So it's not just want to give you the idea that you can do it. And of course, I mean, you have enough background now that you can, I mean, if you just want to get more understanding, you can go and read more about that. So same thing happening in LSTM, for instance. LSTM, which was the older version, pretty much the first gated architecture ever introduced. And this was using 3 different gates, named forget gate, input gate, output gate. Again, if you break it down, you're going to see that essentially what you have are 3 gates, which are 3 linear layers activated by sigmoid. And then at the end of the day, you have a bunch of other linear combinations combined with them. For instance, here, you first compute same as the shallow RNN, one output. And then you compute 2 different gates. One of them is the input gate. One of them is the forget gate. You use forget gate to just gate whatever you had from previous time. So now if you set that forget gate to be 0, then you're going to just close the gate completely. You also use the input gate to gate whatever you got from your current input. So again, if you just put it 0, then you're going to block the input. And then at the very end of the day, you're going to gate whatever you computed at the output as well, right? And then it turned out to be very efficient, working very well. So now, as I said, once again, it's not supposed to be just a simple thing that you totally understand in a few seconds. Just wanted to give you the idea that, well, it's a bit of challenge to make RNN work. And if you want to just get a very dominant model that works, I mean, probably LSTM is the best choice. Yes?
When considering like the different gate values, right?
Yes.
We have different variables associated with it.
Yeah, I mean,
There's the forget input and output.
yes.
So
Yeah, they are totally different. They are different weights.
there are different weights.
Yes.
But when we assign the weights, is it that each, because LSTM can just take this and you append them to you put one at the beginning. I'm forgetting my words here, but you just put them in sequence of each other.
Yes, of course. Yes, yes.
So that's what I'm trying. So that being said, right, does each of them also have to be the same weights? The same way with RNNs, traditionally it's the same weights.
What do you mean by each of them?
Like the get gate and input gate?
No, they have different weights.
Everything
Everything has different. Yes, yes, exactly. So, I mean, here in the diagram, I'm not showing it, but this means that like the first gate you're computing is by a bunch of separate weights. So it's a separate linear layer. Then the other one is another linear layer with separate weights, right?
When we do back update, that's when you have to update all of those weights.
All of them, exactly. So you need to just do the chain rule within the whole gates to just get the gradient with respect to all their weights.
But a generic RNN is not like that, right? A generic RNN is just one set of weights.
Well, you can think of it, I mean, if you think of a general RNN, this is again an RNN, right? Because you have your X, I mean, you don't care what is happening inside the unit, right? You have your X, you have your previous hidden state, you're computing your next hidden state, right?
Sorry, I guess that's a word for some. I guess I meant to say like the other example.
Oh, the basic one, you
Very
mean?
basic.
Yeah, you don't do any gating, right? And then you have just 2 weights, exactly.
Okay.
Yeah.
Makes sense.
Yeah. So, questions? No question? Okay. Moral of the story, RNN. I mean, by doing recursion, you can deal with sequence data, but the issue is that like, the start is easy, the end is hard. So you cannot really train it, and people came with different ideas. One idea which is working with RNN, simply basic idea of recursion, is LSTM. So gating turns out to be very effective. It turns out that really it does this. I mean, LSTM is actually, it was one of the first somehow models with respect to sequence learning, which could work very efficiently, and it was somehow trustable to be used for application like text generation or other things. So for some time, it was its own king. So nowadays, it's just LSTM, but at some point of time, it was something, right? So LSTM is a quite good thing even nowadays for very simple applications, like if you want to just do a price prediction, right? LSTM can do this for you. I mean, as long as it's just the price of, I don't know, oil, right? Something that your gas price, right? You can simply do that when your features are simple, right? And it's still an efficient thing, but at the end of the day, even LSTM or any of those gated architectures turn out to have limited memory as well. So LSTM and all of this gating is somehow trying to expand your memory by being somehow selective, meaning that they are not looking at the sentence and only look at the last window. They might just look at one window here, and then they keep this memory of this window for quite a long time. This is why we call it long, short time memory, right? So you can take this short time memory and take it quite long backward, right? So you can do it with LSTM, but again, this one has some lifetime. So it can go up to some point, but again, is going to somehow vanish. And people started to think about this issue, the issue that even LSTM or any RNN is having that problem, and they started to come up with one idea which we call it attention mechanism. And the attention mechanism, you're going to start understanding it if you understand what is sec-to-sec model. So if you have one encoder which is just dealing with one sequence, then this encoder is going to get all of this sequence in, and it's going to compute some sequence. And when we use basic encoding, we don't care about those ones. We just care about the last guy. You get the last guy, you give it to your decoder, this is going to just generate you one sequence. But people started to say why we should forget about anything happen during encoding. Like whenever we want to just generate one output in the decoder, maybe we can just pay attention to what was coming out of the neural network at that point of time. And this was the idea of attention mechanism. I mean, it's again a bunch of linear layers. You generate keys, queries, scores, and at the end of the day, somehow you connect every single time of your output to all the times in the input, right? And somehow it turns out that it can put attention where in the whole input I should focus on right now. So this was the idea of attention, and once the attention came out, people started to do attention, 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 until a paper came out. It was that attention is all you need. Okay? This is the paper. And that idea was that throw away recursion, actually. I mean, you are doing recursion because you used to do recursion for ages, right? But essentially, when you do attention, you don't need recursion anymore. So just get your sequence, do a bunch of attention on that, get another sequence, a bunch of other attention on that, another sequence, and so on. This was the idea of self-attention. So it's somehow dual to the idea of convolution, but now you do it on the sequences. And if you do that, then you're going to have attention, 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 encoded, attention, 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 decoded, right? And this is what we call a transformer. Nowadays, all of LLMs doing that, okay? So this way it does need a bit of background more, but I just wanted to give you this short story, longest story, very short, that how you can deal with sequence data with no chance. I expect that you totally get what I said, but I hope that given the background now you have on machine learning, it's easy for you to understand the story, right? And that if you really want to do that, that is the topic of other courses or other fields that you can either go on and study it by your own, or you can attend other lectures to learn them more. Okay? Questions? No question? Okay, that's it. So Goodflow chapter 10, if you want to know more about RNN, the basic ones. And also, I mean, we have it in deep learning. There is one course which is called Creative Applications of NLP. This is the one which you can take in fall with Professor Rose. And there you start with transformer. So if you attend that lecture, you have all the backgrounds, but you need to just a bit practice in terms of, encoding, decoding, what is that? You just read through that paper. Attention is all you need to feel confident, and then you can take it. You really don't need necessarily to have deep learning course to take that one. But if you do that, it would be even better, okay? So that's it for today. So next session, just the stories, RL and generative AI, right? And that's going to be the last one. So thanks.